point A. This is point A. So that means if I take this by diagram, this is P. And at some theta angle, I have a sigma R reaction. Okay. To distribute this different theta, I have a different sigma R. And this sigma R is proportional to the component applied in this direction. So that means it is P. And this component will be P cosine C. So the stress will proportional P cosine theta. That means the force component in this direction, P cosine C, right? And the unit is stress. So it's better for me to divide it by some area. And also you can see this stress is inverse proportion to R. For the R very close to the P, the pressure will be higher, right? So inverse to this, inverse to R. Okay? And this is blocking. So it's better for me to times another dimension, thickness. Okay? Create an area, and P over area as a stress unit. Okay? Okay? So this is my estimation about my sigma R. Is it okay? First, this stress proportional to P cosine C. Okay? And also inverse proportional to the R. The bigger of R, the smaller of the sigma R. Right? And I divide by a B, and this is the area. P divided by area is stress level. And I cancel this proportional sign, equal sign with constant to be determined. Right? So this is my estimation about the stress inside. Okay? Now, let's determine this K. So for the integration from K, sigma, okay. The sigma R, the stress, times R d theta, and times the B will be the force in vertical in that direction. Right? The stress times the element, the area. This is R d theta. Times the thickness B is the area times the stress will be the force in that direction. Okay? Okay? Okay. Then this force is vertical component is cosine C. I integrate the theta from 0 to 90 and to both sides, and is equal to P, equivalent with P. Okay. This is a force applied on the sigma R d theta in that area. Okay. This will be the force. And this vertical will be sigma R B R d theta cosine C. I integrate from theta to here. I integrate all the vertical component and both sides equal to the vertical load. Balance with equivalent with the vertical load. That's mechanics, okay? That's called mechanics analysis. Nothing, no magic, very clear and straightforward, just equilibrium. Be careful, we're not equilibrium in stress, we're equilibrium in force. This is force, and this is force. And component, vertical components cosines. And I integrate together. The whole vertical force will balance the vertical force. That's it. Now, if I put this into here, this will go to K, P, cosine theta, E, R. Okay, so let's have a here this will be 2B, 2B, 0 to F pi. Minus K. Oh, this I will put minus because this compression. P, the sigma R will be compression. Okay, so put minus K. Okay, minus K E cosine square theta. Okay, E theta. Right, and R cancel, right, and equal to P. So P. And P cancel 1. So I have 2K 0 to F pi cosine square theta, theta equal to 1. Okay. Then cosine square theta equal to 1 plus cosine 2 theta. Okay. So anyway, finally I can get K equal to 2 over pi. Okay. So the stress at sigma R is equal to 0. This is my circuit. And due to symmetry, the shear tau RC equal to 0 because symmetry. If not 0, and this will plus theta minus theta will have a shear deformation. Okay. Otherwise. And we also can show sigma theta equal to 0 later. Okay. And the only non-zero stress is sigma R. Okay. This is the first thing I want to show you. For play with thickness B, replace the thickness B, and you have a vertical loading applied on top of B. And the stress inside the material at the point is R and sigma point. Now, I want to we also, for this point, it has a coordinate x, y. Right? So at point A, you can have good element. Here. This is R is sigma, and we have the sigma R on this element for any point. Sigma R is positive. Okay? And if I cut this element out, and this element I use the A, B, C. Okay? And anyway, this is just at the point. Okay? But this sigma R theta, or tau R theta, sigma R theta. And this element also have a stress. I use this is a sigma X. Sigma X. And here I have a sigma X. And here I have a stress sigma Y. Sigma Y. Yeah. So I have negative, so it should be because shear will be positive, sorry, yeah. So positive, this is power, so it should be downward. Okay? And this surface is in negative y direction, so the shear will be in this way. Okay? This is the balance of the, because I cut the stress, I cut the element from the domain. Two surfaces parallel to x, y axis, another is in R direction. So this stress, sigma x, sigma y, sigma xy, and sigma r, sigma theta, sigma r theta, they should have a relationship. So now I want to show you how to derive the relationship between these components. In Cartesian coordinate system, the stress, and this in polar coordinate system stress. So how do we do it here? Just for equilibrium, just from the equilibrium of this figure. Okay. Yeah. From this figure, this is C, right? C. Because this angle is C. Okay. So this triangle is C. All right. The theta is BC. So this is positive because this surface, the normal surface in positive x, so the shear should be in the positive y direction. Okay? And this surface, the normal is in the negative y direction, so the shear will be negative x direction. Okay? And this surface with a positive r direction, so the shear will be in the positive theta direction. Okay? Be careful, it's very important. Then we do the equilibrium.